Okay, let's see if anyone is coming in. Testing, testing. Let's see if anyone is coming in. All right. Let's see if anyone's coming in first, and then we'll get started. Showing up. All right, let's get started. Welcome back to STEM Online Academy. Tonight, we're going to replace fear with geometry. So what do I mean by that? We're going to be looking at Gaussian integration, okay? Pretty much, as you all know, an area of calculus that requires a pretty good amount of rigor. As long as you have linear algebra and integral calculus, you should be fine understanding these concepts. All right, so let's get to it. Okay, let's go to the whiteboard. Okay, so screen. Okay, so we're going to do the share screen here. Just give me a moment. Entire screen. All right, and we'll go to the whiteboard. Okay, so as I said, we're going to be doing Gaussian integrals, but in a geometric fashion. So what I mean by that is a more conceptual understanding of Gaussian integrals, okay, and how they work, and how to have the mathematical intuition for solving integrals in general, integral calculus, or anything in calculus for that matter. All right, so let's get to it. So we're going to be looking at this guy right here. This is known as a three-dimensional Gaussian integral. Okay, have any of you ever seen this before? All right. There's a three-dimensional Gaussian integral. Okay, if you know the definition of a Gaussian integral, right? And you can refer to it. Right. I'm going to refer to it in a moment. Okay. So if we have, here, right? So definition. Okay, so this is a three-dimensional Gaussian, right? A triple integral over this over R3. Okay. And what we're going to look at is why this is equal to this, and how we get this triple integral to be pi over a to the 3/2, where a is a real number. As I say that over here, where a, okay, so where I use a different color here, green, where a has to be strictly greater than 0, and a belongs to the real numbers. So a is a constant greater than 0 that's in the real numbers. Okay. All right. By the way, I almost forgot, this is also a New Year's Eve special. So we're going to go lighter than usual. Since New Year's is about the coming together of a new chapter in all of our lives, with fireworks and everything and New Year's resolutions, I thought today would be a perfect day to illustrate that with the conceptualization of Gaussians with simulations, lots of simulations. So we get to check out really cool models, mathematical models, that will help us understand and conceptualize these better instead of actually rigorously solving them. So that's what we're going to do. Okay. Now, we have this triple integral over R3. Okay. And we're looking to show that it's equal to pi over a to 3/2. As I said, we're not going to solve it. right? We're not going to solve it like algebraically, okay? Um, if you want, you can, do it in your own time, right? If anyone has questions or any questions they want in terms of hints. Okay. Right. Well, okay, nothing yet. All right. All right, so let's get back to it. Just want to make sure. Now, this triple integral, as you can see, right, is written in Cartesian coordinates. It looks scary, but it's scary only because it's in this coordinate system. Okay? That's why it's scary. It's not as tricky as you think it is. Okay? Looking at it. Right? So, and let me explain what I mean by that, right? This portion here, anytime when you see these x squares plus y squares or x squared plus y squared plus z squares, you know you have to do some sort of a change of coordinates type of approach here, right? So this guy here. But let me show you what that looks like geometrically, at least for the function e to the x squared plus y squared plus z squared. Okay, let's go to the desktop. Okay, I'm going to get out of the share screen. Okay, so let me get out of share screen. Sharing. And what I'm going to do is, just give me a moment. We're going to go to our first simulation. Okay, so on my desktop here, we have the simulation. Okay. By the way, if you have any questions, please let me know. I'm going to make sure that you guys can see it. Any questions? It's a quiet night. I guess people went out for New Year's. Let me see. Anyone at all? Okay. Anyways, let's get on with the live show anyways. So let's get back to it. Okay, I'm going to share a screen because I want to show you that simulation of a Gaussian function in terms of x, y, and z. Okay, so we have the entire stream here. Okay, let's go to it, to the window. Okay, as you can see here, right? So let me just rewind. We're looking at a Gaussian cloud. That's what this is. E to the whole power of e to the negative whole power of x squared plus y squared plus z squared, right? So here's what we're dealing with. This is going to give us a better conceptualization of what's happening. So we have a bell curve. If you guys know what a bell curve, that's e to the negative x squared. And it's like, it goes up and down, right? Here we have e to the negative whole power of x squared plus y squared divided by 2 sigma squared. Okay. Now, you can see what's happening with this type of surface. It's a surface, obviously, right? Because why is it a surface? Does anyone know why it's a surface? Right? It's a Gaussian cloud, but why is it a surface? Why is it a surface? It's a multivariable function. That's why it's a surface. It has 2 or more variables. That's why it's a surface. Okay. So that means obviously it would be in a 3-dimensional space, right? Here you can see that it's a sheet, right? It's a sheet that bends upwards in a 3-dimensional shape. Now it could look like it's not a manifold for those of you who are advanced. My book mentions manifolds, but that's for later. It's not a manifold. It's just a regular surface, right? E to the negative whole power of x squared plus y squared over 2 sigma squared. Okay. All right, so let me go back here. Let me rewind. Okay, so we have here, right, our Gaussian cloud, right? That's what this is, right? And you can see that x squared y squared, those are the x, y coordinates. The sigma represents the standard deviation. So if those of you who have taken statistics, you know what I'm talking about. Okay, so in statistics, they talk about something called the standard deviation, right? It's the measure of spread, measure of the spread of certain quantities on the bell curve. And that's the sigma. Now, there's also a thing here called the sigma square value. Okay, sigma squared. Right? Sigma squared is what? Anyone know what it is? I talked about sigma being the standard deviation. What's sigma squared? Let me stop sharing for a moment. I need to see if you guys understand what I'm talking about. Okay, so nobody yet. Share screen. Okay, let me go here. Let me go back. Let me go back to the window. Just 1 sec. I just had it. Okay, 1 sec. There we go. Okay, I'm going to share it. So my point, right? So we have this Gaussian, right? We have a Gaussian Gaussian surface, right? A Gaussian cloud. That's what this is called. E to the negative whole power of x squared plus y squared over 2 sigma squared. That's what a Gaussian cloud is. And what the cloud is, right? It's a 3-dimensional bell curve. Okay. So a bell curve is a function, let's say f of x equals e to the negative x squared. You should be able to know that. You should know that, right? That a bell curve is always in the form f of x equals e to the negative x squared. Okay. Part of a PDF. Now, this has been extrapolated to two-dimensionals sorry, 3-dimensional space, right? With a multi-variable function of x and y, right? That's why it's in three-dimensional space, right? So now you have a bell curve, right? That is on all x, y, z coordinate axes, okay? Right. So you can see here, if you rewind again, right? Okay. Let me just go here. I can play it. Okay, so you can see what's happening, right? So let me just rewind. I'm rewriting a lot, just waiting for people to come in so I don't want to go too much through the material if I don't have that many people. It doesn't really make sense. Again, also Happy New Year to anyone who's coming in, because this can be shown anywhere. Probably other parts of the world is already New Year's, so yeah. Okay, let's do it again. All right, so as I was mentioning, right, we have a Gaussian cloud, right? Okay, so we have a Gaussian cloud in 3-dimensional space. Okay, that is a bell curve. That is a bell curve function in multivariable. So it's not a bell curve. It's a surface now, right? So it behaves as a surface. It is a surface because we have 2 or more variables, right? So we have it raised to the negative x squared plus y squared over 2 sigma squared, as opposed to a bell curve, which is e to the negative x squared. Now, what's this sigma mean? Again, anyone coming in, we're talking about the three-dimensional surface here. Okay, 3-dimensional surface of a bell, right? A Gaussian cloud. I want to talk about. Okay, let's see if anyone's coming in. Just give me a moment. Okay, anyone in? Not yet. Okay, let me continue. Okay, so let me share screen again. I'm going to go back and forth. I need to see if people are coming in. Okay, let me go back. I'm going to share screen again. Okay, let's share. All right, so again, so the point of this Gaussian cloud, right, is to give you a geometric conceptualization of how Gaussian integrals work, why they work the way they do, and how you can make them easier for yourself. Because at first, when you saw one, these look weird. They look a little bit intimidating. They're actually easy, but at least this gives you a better understanding why the coordinates that we're in are an issue, right? We just need to do a change of coordinates, to make our integral easier to calculate. Okay. Right, so let's rewind here. Okay. So we have an XYZ axis again, right? A bell, normally for a bell curve in the form of e to the negative x squared. Okay. Right, e to the negative x squared in 2-dimensional space on XY axis is a bell curve. Here in 3-dimensional space, again, we have it as a multivariable function, okay, in terms of x and y, right? Y is in terms of x and y. Y is the surface. How do we know that a surface has to be more than one variable? Because multivariable functions, right, are surfaces. They're surfaces of some sort, right? That's exactly what they are, okay? Right? And you'll notice another thing too, that this Gaussian cloud, right? It's written in the form e to the negative x squared plus y squared over 2 sigma squared. If you've noticed, it looks like a certain type of distribution. That's a good question I just brought up. So the function that we're dealing with, the e to the negative x squared plus y squared over 2 sigma squared, the Gaussian cloud, what type of distribution is this? What type of distribution function, to be more accurate, because it's a function too, function of two variables. If anyone can figure out what it is, it's going to be free tutoring services for the first 2 lessons. Yes, I do offer tutoring lessons. Okay, let's go back. So again, we have this Gaussian cloud here. Okay. You'll notice that it's a certain distribution function. I like rewinding it. I don't know about you guys, but it's a very good surface to be looking at. I'm sure the audience can agree, hopefully. Okay. Right? It's just a sheet, right? You take a sheet throughout the XYZ axis, right? And the surface you can see is going up and down. Now, another thing too, depending on the variance controls the cloud width, okay? So I'm gonna let you guys, I'm talking about something else here. I'm gonna let you guys still think what type of distribution function it is, okay? All right. At the same time, right? If you look at the bottom here, again, if we do this, right? You can see that the variance sigma squared controls the width of our Gaussian cloud, right? So depending on whether sigma and sigma squared are increasing or decreasing, seems to affect the cloud width of the Gaussian cloud. Does anybody know what type of probability distribution? Oh, I just mentioned it. Yeah, sorry guys. Yeah, I just mentioned that. It's actually a probability distribution. A probability PDF, they usually call it probability distribution function. Okay? That's what this is. Okay? Right? Because the probability distribution function is always written in terms of e to the negative whole power of x minus mu all squared divided by 2 sigma squared. Right? Where x in this case is that x plus y squared. We don't have a minus mu. The mean here seems to be 0. As I said, sigma squared is the variance, sigma standard deviation, mu mean. The mean mu is 0 here. I don't seem to have a mean. And then xy is just xy coordinates. Okay, so hopefully this gives you a better understanding why we need to make a change of coordinates. Right? Why do we have to make a change of coordinates here? Because we have x squared plus y squared, right? This is y squared in the exponent. Anytime you see x squared plus y squared and you're doing some integral, just change it. Change the coordinates, right? Change it into some sort of polar form or some other form that requires the x squared plus y squared. You can make it a singular function, make it easier, okay? All right, so we're done that. Okay. So let me see what else is on the menu. All right. Okay, so we looked at a three-dimensional. Let's go back. Let's go back here. I'm going to try and get out. I'm going to get into share screen. Just 1 second, guys. I'm going to share screen again. Share screen. Go to the entire screen. Here. And we're going to go to the whiteboard. Okay, so we've got the whiteboard here. So we were looking again, right, at the definition, right, of a three-dimensional Gaussian. Okay. So three-dimensional Gaussian over R3 of e to the negative a parentheses x1 plus y squared plus z squared. We were looking at this person here in our graph, right? And this type of function here. Okay. Right. Now I'm going to give this, we're not going to solve it because we don't have time to do problems of that rigor all the time in live shows. Okay. We want to talk about what's going to help you and help the audience and people in this niche of mathematics that are common mistakes, common misconceptions. So we want to get straight to the point. Okay. So we won't always be able to solve these right on the bat. There's not that much time, right? Even though it's like around an hour and a half or 2 hour live stream. Now I can give a hint though. So here's a hint. Okay. Hint. Hint. The way to solve this is to use the definition, right? Definition of a Gaussian, right? So definition. So definition DEFN for Gaussians. Okay, for a Gaussian. And the Gaussian is defined as the following, okay? If you have an integral I and it's equal to the integral, right, of, let me just move this around, integral of negative infinity to infinity of e to the negative ax squared dx. This is equal to square root of pi divided by a, right, times e to the b over 4a. Okay. What I mean by a, this is the a I'm talking about here. It's going to say little a minus capital A. Okay. This would be b squared. B squared, right? That's your hint. Use the Gaussian integral to figure out how to do this. Okay. Make sure everyone is on the same track here. Okay, we have anyone coming in. It's all right, so not that much of a audience today. Okay, so let's continue with definition. We're going to look at something else here, right? We're going to look at something interesting. By the way, if you guys have any New Year's puns, please put them in the chat. Okay, New Year's jokes, or even New Year's resolutions you want to discuss, right? Okay, so I want to get to know my audience. I always like to get to know the audience or viewers or whatever, right? Okay, so now this, we're moving on to the next thing here. Okay, so on our schedule, we've talked about how our New Year's Eve theme is, why Gaussian integrals, right, are becoming scary. Okay, let me see here. We also had something else. If I included, I believe I did include it. I think it was number 3. Okay. Number 3. Have we talked about that? What else? Yeah. No, where are we? Okay, we're going to look at the geometry of Gaussians in 3D. Yes, you may be thinking, we just discussed that. No, we did not. We're getting much deeper into it. Okay, I'm pretty much getting into the skeleton of the conceptualization when it comes to the geometry and critical thinking aspect of Gaussian integrals. Okay. All right. So let's look into that more deeply. All right. So I think what we're going to do, right? Because Gaussians, yes, they're a radial mess, but they're concentrated near the origin. They're a radial mess, but they're concentrated right at the origin. Right? So what do I mean by that? Okay, what do I mean that it's a radial mess when it comes to Gaussians? Okay, so let's go back to the desktop. Okay, back to desktop. Okay, and we're going to look at something else here. Okay, so let's exit out, stop sharing, and we'll go right back. Just give me a sec. Get rid of this. And we're moving on to the next one here. Okay. All right, just give me a sec here. Always going from multiple screens can be a bit annoying. Okay. Let's see, sharing the screen. Nope, there we are, media player. Okay, so here we go. All right, now we're looking, right, at a Cartesian grid. Okay. These are spherical shells, right? So the Cartesian grid implies we get spherical shells only, right? These are, if you've taken some form of, doesn't have to be multivariate calc, it can be even Calc 2, sometimes they teach it depending on the curriculum. This has to do with level curves, okay? The level curves are, or level sets are just circles and, multiple circles, concentric circles in two-dimensional space. Okay, we use level curves when we want to graph three-dimensional surfaces, like I mentioned earlier, a Gaussian cloud or anything else for that matter. Okay, so if you look again here, so we have to rewind. That's paused. Let's go. So we have a Cartesian grid. Okay. And our level sets or our level curves here, right? They're concentric circles, right? Each with increasing radii from the center of the origin. Okay. If you get rid of the grid, right, we're just left with the spherical shells. Okay. So these are actually spherical shells, right? If once we get rid of the grid. Okay. So I hope this is helping in the breaking down of the mathematical modeling when it comes to three-dimensional Gaussians, right? That's what we're doing. That's what we're analyzing, is trying to analyze and trying to gain a strong mathematical intuition on three-dimensional Gaussian surfaces, okay? How they look and how they behave, right? So again, I'm going to rewind again. Right, so again, we have a Cartesian grid, right? Right? And we have our level sets or level curves there on the Cartesian grid, okay? And if we get rid of the grid, we get just spherical shells that are remaining, okay? Let me make sure, just want to make sure, I shouldn't stop sharing. Let me see if anyone's saying anything here. Anyone in? Okay, not right now. All right, so we just continue. Okay, so make sure. So again, I know it's New Year's. That's why we're getting not that hardly anyone coming in. Right. So we got Cartesian level surfaces, level curves. Sorry. Okay. Anyone have questions? Remember, it's a live show. I need questions. When you give me feedback, it's better, so I know if I'm doing a good job, how I need to do it, what you want done, what you prefer. Right. Otherwise, I'm left in the dark, sort of. Right. I don't know about you guys, but just watching these videos are nice. Be pretty entertaining, especially if you like any form of geometry. Even though a lot of times in math it can get very abstract, but it doesn't have to be geometry, the subject geometry per se. Geometry is everywhere in math. Doesn't matter the topic. You'd be surprised where geometry and mathematical modeling comes up, right? Okay, so as I said, we have a Cartesian grid, right, in the XY Cartesian axis coordinate system. And we have our level curves and level sets that we've drawn on the XY axis, okay? Once we've gotten rid of the grid, right, we just have spherical shells. They can be interpreted as spherical shells, okay? And the reason for that is, one, once you get rid of the grid, uh, the, the perception is now, it doesn't have to be in 2 dimensions. This can be a 3-dimensional surface, right? Because it can be interpreted that way. That's the first thing. The second thing is that when you don't have the grid lines and any of that, it's just, an overlapping of spherical shells, right? That's the way to think about this. Okay, so let me just get out of this for now. Let me see if anyone's in the chat. Okay, not right now. All right, welcome. This is a New Year's Eve special. Hope you're enjoying what is going on. We are doing. We're talking about Gaussian integration in 3-dimensional space, but from a geometric point of view, using modeling. Okay. All right, so we're going to go back to it. So let's go to share screen. Okay, I'm going to go to share screen again. Okay. And we're going to look at, let's go over here. Okay. Going back to the whiteboard. Okay, so we've looked at Gaussian integrals, right? That scares students off, not to be that intimidated. Now we looked at the geometry of Gaussians in 3D. To more say we did. However, though, I don't want to really check this off. Okay. There's some other partitions of Gaussians in 3D that we need to look at. Okay. Different types of surfaces and curves to sort of get your visual spatial reasoning up to date. Okay. Because calculus is more than formulas. It helps if you have a strong geometric understanding. Okay. Yeah, and especially, that's right, especially when it comes to the problem solving aspect. But even if it's just for an abstract problem, not all abstract problems require you just to use the equation. Quite often require some sort of strong intuition. Okay, that's why I keep emphasizing having some sort of strong intuition when it comes to math is very important, and that's what I hope to strengthen. Okay, especially for undergraduates. Okay, so we're going to be looking again, right? Geometry of the Gaussian in 3D. Okay, and I had the list here, what I wanted to discuss. Are we on? Oh, yes, we are done. Okay, we've done that one. We can look at spherical symmetry. And when I mean spherical symmetry, I'm talking about actually seeing the integral. No, it's not what you think. It's not actually calculating the integral. This time, we're going to see visually the integral, okay, by spherical symmetry, okay? So let's get to it. All right, just 1 second. So let's do that. So let's go back to the desktop. Okay, let me just go back here. We're going to get out of the share screen. Stop your screen. Okay, just give me a moment, guys. 1, 2, 2, 3. Okay, we're going to be looking at just 1 second. Someone's contacting me here. Is any questions on? Okay, so someone was asking. Okay, so let's get to it. I thought someone was asking a question on my phone here, my phone and the chat as well. Yes, Happy New Year's to you too. All right, but besides that, back to spherical symmetry, okay? So if the function is only depending on distance, right? If it only depends on distance, pretty much the angles won't really matter when it comes to spherical symmetry, okay? Let me explain what I mean by that. So if you have the iso surfaces, okay, what that means is we have spheres, right? We have spheres within spheres within spheres, it could be n number of spheres. In this case, the problem that I've set up here, right, is isosurfaces. Okay, so those are nested spheres, right? And you can see I've color coded the spheres, right? Inside is the smallest sphere, obviously with the smallest radii from the origin, right? And as you move outwards and the spheres expand in size, obviously the radius will expand in size as well, right? So what you can see here is that you get different variabilities in terms of our spheres here. What do I mean by that? What do I mean different variabilities or variations? Well, isosurfaces, right, are pretty much spheres of equal, right? Let me repeat, equal volume. Okay, they all have the same. They all have the same volume. Now that can be a bit. Paradoxical, okay? Because you think, okay, the size. We have multiple spheres inside of spheres. If if the smallest one must have a different volume than the other ones, right? Depending on the size and the radius. So why do they have the same volume? You're thinking. Why are you saying that? How does that make any sense? Okay. Well, think about it. What does ISO mean? What does it mean? What does ISO mean? It means the same. That's exactly what ISO means. It's the same. It's the same sphere. So even though we have surfaces, the nested spheres, right? Nested spheres, right? They're all going to have a equal value. Yeah. Equal value, not volume. Yes, I have to correct myself. Sorry about that, guys. Yes. Yeah. Have to correct myself. Not volume. Value. They all have equal value. Obviously not volume, because that wouldn't make sense, right? As the size increases, the volume will start to increase, right? It's not possible any other way. It wouldn't make any sense. So as the so the isosurfaces all will have the same value. Okay, that's what this simulation, the mathematical model shows us, right? Now, another thing that it shows us, right, is that based on the color, right, of each of these spheres, right, different colors is encoding the density. Okay, and what do I mean by that? Well, the bright part, right, is fading outwards, right, as you can see here. Okay, as you can see, I've given you guys a panoramic view. Panoramic is a good word. Panoramic view of how the isosurfaces work, right? Like a complete rotation on the XYZ axis of all these isosurfaces, you know, behaving and inscribed in one another, right? So I think it's pretty cool. Good. I'm going to play it again, right? So again, we have isosurfaces, okay? Right, so we have multiple spheres with obviously color-coded densities. I did that because each one has a different density, right? If we were to calculate the density, how do we calculate the density? By the way, this is a grade 8 problem now. I've made it, that question right there I just made very easy, right? Since each sphere, right, of the isosurfaces has different spheres of different volumes, okay? Obviously, they have different volumes because of their size, right? So the greater size, the greater the volume. Now, if they all have different volumes, right, then their densities have to be different as well, right? Right? Because density is equal to mass divided by volume, right? Each sphere will have its own mass and volume, okay? So all you'd have to do is use density equals mass divided by volume, okay? And that's how you would be able to determine the density of each of these spheres, okay? So you can see what I mentioned is that the angles don't really matter here as much. when it comes to the isosurfaces. They're of equal value everywhere. Okay. And what I mean by that is this that when it comes to these isosurfaces or the nested spheres, right? You can, what I mean, the angle doesn't really matter. I mean, think of it in terms of XYZ coordinate axes, XYZ coordinate, which we're on, with XYZ coordinates, right? So we have longitude, latitude, and all that, altitude, right? You can find a specific spot, a specific point with XYZ coordinates, right? Okay, at a specific location on these nested spheres. Okay. So again, complete panoramic and peripheral view of the conceptualization of isosurfaces. Okay, it's pretty cool stuff. Right. So the mathematical model, right, gives you like a full deep understanding of how isosurfaces work, right, and why they're important in the first place. Okay. Let me see if we have anyone coming in. Right, so this is isosurfaces. Okay. Right. Density, and the density is either high or low, right, depending on the mass and the volume, right, for each surface. Okay, let's get back to it. Anyone in? Hello, Happy New Year. Anyone who's come in? I see we have one person in. You got 2 people in now. Good. Okay, come in. It's New Year's. Happy New Year. Happy New Year. Happy New Year. I hope to hear from you back. Okay. It's a special New Year's Eve presentation of mathematics. All right. So we're going to be looking at, as I mentioned, today is Gaussians in 3-dimensional space, but from purely, not an algebraic approach, a geometric and a visual spatial understanding of Gaussians in 3-dimensional space. Okay. Let's go to it. So I'm going to share my screen. Okay. We were looking at the whiteboard. All right. We go to the whiteboard here. By the way, say something in the chat. Hi, Happy New Year, or anything. That'll be handy so I can communicate back and forth with the audience. All right. In the meantime, we're looking at the menu. Yes, our menu today is this, right? From 1 to 10. We've looked at why Gaussian integrals can scare students, right? I gave I showed an equation that was a little scary, and I made it simpler. Well, I didn't actually algebraically solve it, but I gave a geometric understanding of why we would need to convert to different coordinate systems. Okay. Number 3, we looked at the geometry of Gaussians in 3-dimensional space. Okay. Then we also looked at spherical symmetries as well. Okay, because quite often when you deal with Gaussians in 3-dimensional space, you have to do a special type of spherical symmetry. What that means is putting it into some sort of a polar form, either polar or spherical form, coordinate system of some sort. And that's why I wanted to show you guys that model, because to prove that it is the mathematical model is a sphere. When you have anything in a spherical form, like in general, you want to switch to spherical coordinates quite often. Okay. All right. So hopefully that model makes things easier. Now we're looking at volume elements and radial collapses. Okay. So what do I mean? Volume elements and radial collapse. We're going to be looking at something like this. Let's go to it. Let's go to the whiteboard. Not the whiteboard. I'm going to go to the desktop. Okay, let's go to share screen. No, that's not it. Just give me a sec, guys. One Where were we? 1, 2, 3, 4. Okay. Just give me a sec. I just want to make sure everyone is on the same page here. Yeah, just give me one moment. We have someone else. I like when live shows when I can communicate with people since we don't have that many viewers today. Okay, so we're going to be looking at, right? We're going to look at volume elements, right? We're going to look at volume elements and radial and volume elements and how the radius collapses pretty much, right? So what I mean by that is that all dimensions collapse into one type of radius, okay? So let me talk about that. If there's no questions, please ask questions. That's what a live show is for, right? Questions. It's your opportunity to give me questions. Okay, so we're going to be looking at rotating the Gaussian, okay? So again, I'm going to play the live video here. So you'll notice that this model looks really cool, right? We've got a rotational Gaussian, right? And our integral remains constant, unchanged. Now I give a two-dimensional a view of how this works, but I also give a panoramic view of it as well, right? And the reason why I need to show you guys that is because I want to prove that it's actually key word here, if anyone can fill in the sentence. It's actually what? What is it actually? If if I keep rotating my coordinate system, right? Then there is some rotational blank. It's a special word, right? Right. If I have to keep rotating my coordinate system, regardless of how I rotate my coordinate system, counterclockwise, clockwise, vertical, diagonal, doesn't matter how I rotate this Gaussian, okay? Regardless of how I rotate the Gaussian, right? This integral, right, is something called rotational invariant, okay? That means that it's kept constant, okay? Right? The integral is constant. It's unchanged, okay? And the angles don't matter. That's what this is a continuation of what I was saying earlier, that the angles do not matter when it comes to distance, right? Because regardless of how I rotate the Gaussian, right? And when you're rotating anything, that means there's some sort of, angular displacement, right? There's an angle involved into rotating it, right? Maybe 0 degrees, 360 degrees, 720, doesn't matter. Regardless of how I rotate the orientation of my coordinate system, right? The integral of the Gaussian remains constant, remains unchanged. And that means that it's invariant, okay? So that means that the integral remains invariant, all right? Anyone have questions so far? Let me see if you guys are having questions. Anyone having questions? Anyone enjoying the content? Okay. Right, again, we're looking at rotating this Gaussian, okay? For anyone new coming in, let me repeat, right? I'm trying to show why that following integral there over R2, okay, of g of parentheses x squared plus y squared dx dy is invariant. So why is that integral invariant? And what does invariant mean? Invariant means constant. The integral is constant. Now, why is it constant? For anyone new coming in, that means you probably didn't hear the hints that I gave. There was an integral over there. Can anyone explain why this integral is constant or invariant? This is synonymous for constant. Rotating the coordinates, right? Rotating coordinates will not affect it whatsoever, yes, but there's a hidden word here I want to hear. Anybody knows? Let me rewind again. So regardless of how I rotate my coordinate axes, right, in the xy plane, my integral will remain invariant that I've highlighted over there, okay? Regardless of how I'm rotating the axis, that's what the mathematical model or simulation is showing, right? Regardless of how I rotate counterclockwise, clockwise, diagonal, doesn't matter how weird I rotate it, that integral will remain invariant. Okay? It's because the rotation does nothing to change the integral. And since the rotation does nothing to change the integral, that means that the angle does nothing to change the integral. So the angle has that much, it has hardly any importance here. The angle is pretty much can be faded out. That's why it has to fade out here. Okay, if that makes sense. Yeah, right. If anyone has any questions on that. Okay, as you can see here, again, we're having our entire xy axis, right, being rotationally invariant. Okay, so the integral remains constant. So it doesn't matter how I rotate my coordinate axis, the integral will remain strictly constant. Okay. And that's because it doesn't matter how I rotate at what angle, the angles don't matter here, right? The integral remains constant. That integral that I've highlighted over there in a rectangular bracket is going to remain strictly constant. Okay. All right. So again, let me just put the halfway. I'm going to do this halfway here. Okay, just 1 second. As you can see, rotating doesn't make a difference. So that means the angle doesn't make a difference. So the angles are pretty much faded out. All right. So rotating the Gaussian doesn't matter how much you do it. It really doesn't. The radial distance is what matters. The angle doesn't matter as much. Okay, it really doesn't matter. And again, as you can see here, I've highlighted my integral, right? That integral remains constant or invariant, you can say. It's synonymous, right? Because it doesn't matter how much I'm rotating my coordinate axis, the integral will not change. That's why it's an invariant. Okay, it's a rotational invariant, right? And rotating this Gaussian doesn't matter. The Gaussian will stay exactly the same. This Gaussian integral doesn't matter. It will stay the same because it's invariant. Okay. All right. So let's get at this. We're going to go to whiteboard and see where we're at, what we need to check off. Okay. So let's go back to share. I'm going to share my screen. Entire screen. Okay. And we're on the whiteboard. Okay, so we talked about volume elements, radial collapse. We're at the halfway point now. Okay, so I think it's appropriate to talk about where the gamma function appears. Okay, let's go to page 2. I want to show you something, a definition of the gamma function. For those of you who know what a gamma function is, or you learned about yourself, or you learned it in my past videos or live shows, talk about the gamma function a lot. It's one of my favorite integrals, actually. If you're studying integration, you need to know what the gamma function is. There's no excuse. In applied mathematics, if you don't know the gamma function, something is wrong with you. Okay, so the gamma function is the following. Okay, the gamma function calculates, right? Calculates an improper integral, right, of the product of a variable x to the power of n minus 1 times e to the negative x dx, where n is some value, some number. And this ranges. What I mean by value or number, it could be it could be a whole number, it could be integer, it could be any of those, right? It can be a fractional value, right? More about how to calculate the gamma function of fractional values in my other You have to find it in my other live shows or streams. So those of you who want to look into that, please go into my other streams or live shows, okay? For more of a detailed and more rigorous mathematical explanation of the gamma function. So here's the gamma function, okay? Right, we want to look at the gamma function. Now, as I mentioned on the list, right, where the gamma function appears, right? That's what we're going to talk about. Where this gamma function appears. Okay. Just 1 second. We have someone here, I think, asking a question. No, that's not it. No. I think we talked about that. Where are we now? No, that's not it. Yes. Okay, so I thought someone was contacting. But anyways, we know that the gamma function, right, as I was saying, calculates a certain type of improper integral x to the n minus 1 e to the negative x dx. But they also measure how fast the mass accumulates so quickly. That's right. In physical terms, it can calculate how fast the mass accumulates. Okay, that's what the gamma function can do. So let me demonstrate what I mean by that. Okay, let me get rid of stuff here. We're going to go directly to a simulation. Okay, so let's go to a simulation. Going to the whiteboard, the desktop. Just hang on for a second. Just give me a moment. I'm going to show you something really cool here. Okay. All right, so let's look at, I'm going to share screen. Share your screen. Okay. And I'm going to answer why we get that mass accumulation when it comes to the gamma function. That's what it measures. Okay, so let's look at, was this it? Just give me a sec. We have someone. Sorry for the interruptions. It is a live show. Anything can happen at any time. Let's see here. No, where are we? This is the wrong one. Just give me a second, guys. I have the wrong simulation here. Just give me a sec. I'm just going to find the right simulation. 1, 2, 3, 4. I think I've got you. Let me see here. Am I losing track of which ones I had? I have a lot of simulations I want to show on this live stream. Nope, that wasn't it. I think it was that one. Was that it? No. Let me see if it was this. I was trying to find it. Oh, yeah, I got it. Yeah, here it is, simulation number 6. All right, guys, I'm going to share my screen. Okay. So I'm going to share the screen. Okay, so what we've got right now, all right? What we've got right now is we've got a radial integral, okay? And what I mean by a radial integral, right? I'm talking again of a gamma function, right? I put there the definition of a gamma function. Notice what's highlighted in orange, right? Okay. So highlighted in orange is our radial integral gamma of S. That's the definition of the gamma function. I wrote it the same way. This variables, same thing. It's an improper integral. Okay, and what we're calculating what I'm geometrically trying to show you is that as we have a radial integral, right? This will transform into a gamma type of curve. Okay. So there's the gamma, right? The gamma function, right? As a shape, it's a shape accumulator. So radially on the xy plane, it's concentric circles coming out from a radius from the origin. But then when it's mapped onto becoming a smooth gamma curve, right? So again, concentric circles, coming up one by one, right? And then what happens is, right, these concentric circles, okay, they can be mapped. What ends up happening is that's a radial integral, those concentric circles, what it's modeling, that's a radial integral. That radial integral is then mapped onto becoming a smooth gamma curve, okay? And that gamma curve is on the right here, highlighted in orange, okay? Right? Underneath that orange curve there, right? Obviously, what's underneath the orange curve? What geometrically are we measuring? Those of you who've taken calculus should know what that means. Orange curve, the region under the orange curve, bounded by from 0 to, let's say, r. Geometrically, what are we measuring? Anybody knows? Anybody knows? Just measuring the area, right? That's what we'll be measuring, okay? Right? So as you can see here, we have a radial integral, right? Again, I'm going to explain radial integral. And that radial integral can be modeled by those concentric circles in the xy plane, right? Or level curves in the xy plane, to be more precise, because level curves is a function of two variables, where we set one of the variables equal to some constant. So that's why it's a single variable function, right? That's why we get that those concentric curves there, because they should be one variable circles, okay, in the xy plane. Now that model of the concentric circles of the radial integral can be mapped on, right? And they give us something interesting. They give us a smooth gamma curve, okay? Now the gamma curve on the right hand here is labeled in orange, okay? And you can see that it's moving, it's swerving back and forth, okay? I'm highlighting the right part here, by the way, just to show you that's the gamma curve that we're dealing with, okay? And the point of it is to show that that orange curve, right, the gamma curve is a shape accumulator, a mass accumulator, right? So geometrically, it's a shape accumulator, but physically, if you're talking in terms of physical applications, the radial integral or the gamma integral actually measures accumulation of mass, actually. Okay, that's the application of the gamma integral on the right here. Okay. Okay, so I think we've gone into that part. Let's go back to the whiteboard. Okay. Let me just get to share screen. All right. We're going to go to the whiteboard. Okay, page 1, see where we've checked off. We talked about that. Okay, the gamma function appears. We're going to look at the Gaussian as a mass in 3-dimensional space. Okay, so Gaussian is mass in 3-dimensional space. So what do I mean by that? He's giving me a friend of mine's annoying, keeps sending me New Year's messages. Let me see what he's going on about. By the way, leave something in the chat that can make all of us laugh. That would be nice. let's get back to it. So I want to mention something. Most mass lives in the shells, not at the center. Again, let me repeat. All mass, right, lives within the shells, not the center. Okay, not the center of the surface. Okay, physically, anyways. All right. Those of you who have done any physics classes, you probably know, right? Because this is an application of physics. Those of you who've done any physics classes, you probably understand what I'm talking about with shells and stuff like that. We're not now. It's not what you think. We're not looking at moments of inertia, even though that's another topic. But I don't want to digress. But even in those topics, they talk about shells and stuff like that, and lambda densities and stuff like that that's related. But the point is that if you have a Gaussian, right, a mass in 3 dimensions, right, the mass is centered. It's not centered in origin. It's centered. It's not centered in origin, but it's within the shells. That's where the mass is. Okay. If that doesn't make sense, let me give you a visual description of what I'm talking about. Okay. So let's get right to it. Okay, so let me get out of here fast. Okay, let's go to the let's go to the desktop. 7. Okay, so okay, so we almost got it. Okay, so let's go to the window. And we're going to go to the media player. Okay, so media player is up. So this is what I wanted to show you, not only in terms of a physical application, right, but also in terms of a probability and statistics application too, actually, right? So you can see in this graph here, okay, probability, right, probability mass versus radius. So now this is very interesting stuff that we can bring alive, right, in our applied mathematics framework, okay, as you can see here. So you can see on the left-hand side here, we have the concentric circles. Okay, let me just rewind this. Probably have to rewind it. So left-hand side, we have the concentric circles or our level curves, right, in 2-dimensional space, right? Okay. And you can see that shell, the blue-green shell that was highlighted, is expanding. It was a small ring, and then the ring got really, really big, so much so that it's completely out of the XY axis, but I hope you get the point, right? I'm going to explain what's happening, right? In other words, we had a thin shell, right, with radius r. That's the highlighted the blue-green curve, okay, that keeps expanding. And this is mapped on, right? It's mapped on by a probability mass versus radius, right? So what's happening is pretty much with that shell, as r is moving, right, as the radius is moving, okay, or as I should be more precise, maybe. Yeah, let me think about my words. As r moves, but as r expands, I should be saying, because as the shell is increasing, the radius is expanding, right? As the radius expands, you can see that we have on the right-hand side a graph, right? Right here, our probability mass density graph, okay, which shows our location of the mass in the shell, right? And that's dependent on how big the radius is getting of our ring there. Okay, so as the ring expands, right? Okay, so as the ring expands, okay, as our ring expands, right? The thin shell space and radius r as it expands, right? Then our probability mass versus radius graph, right? That little orange dot there, right, that is moving along the probability mass density curve is moving, right? Its location is changing depending on the increase of radius of our shell in the space on the left-hand graph, if you understand what I mean, right? So as that shell is increasing, right? Again, let me show you again here. Right, as our shell is increasing on the leftmost part here, okay? Right, you can see it's increasing, okay? As that shell is increasing, blue-green curve. On our right side, probability mass versus radius, the mass in this shell, that point there, is following its trajectory is moving. So the location is always changing, okay? So based on the radius of that shell, is telling us where the location is changing on the probability mass versus radius curve. All right. Let's go back here. Put likes in the chat button for anyone coming in. Likes or New Year's. Happy New Year's. If anyone's coming in. Okay. Let's go back to, let's go back to it. Okay. I'm going to go back to the whiteboard, I think. Yeah, but I first have to share entire screen. So that, and we're going to go to the whiteboard. Okay, so we've talked about simulation mass and thing. Ah, yes, we're getting to something interesting. A real, tangible, and interesting physics application called the Maxwell-Boltzmann distribution. Now, yes, for those of you who don't know, right, all these this concept is in my book, Advanced Integration Techniques. It's a mathematical methods book, right? But it's mathematics, right? But you know, applied to physics and engineering. Right? That's what this book is about. Right? So this book is very interesting. It's advanced mathematics applied to physics and engineering. Just for those of you who don't know, and that's why you're seeing some of these physics applications coming into play here. Okay, so we have a interesting physics application, Maxwell-Boltzmann distribution. Okay, you don't need to know what it is per se, but you do. It's good if you know what that integral is. Okay, so let's go to it. A little backstory on the Maxwell-Boltzmann distribution. Okay, Maxwell was a theoretical physicist. Okay, responsible for his discoveries in electromagnetism, specifically the Maxwell equations. Won't go into those. Has nothing to do with this. Just telling you a little bit about Clerk Maxwell. And Boltzmann was also a physicist as well. Specialty was in thermodynamics. Okay, not going to give that much of a backstory, but there's a distribution that uses both their names, the Maxwell-Boltzmann distribution. Okay, and there's a number of equations that we look at. Right, so equation one, right? Equation one of the Maxwell-Boltzmann equation is the PDF, right? The Maxwell-Boltzmann equation, for those of you who know what a PDF is, I mentioned it earlier, and you should know it from high school, is the probability density function, okay? So again, it's a bell curve in a two-dimensional space because we only have v f as a function of v. So this would be a two-dimensional space curve, okay? So f as a function of v being the velocity, by the way. So mention what these are. V is velocity, m is mass, k is Boltzmann's constant, and T is the temperature. Okay. I digress. So as I was mentioning, right, this is the PDF that we're dealing with. It looks fancy, it looks a little scary. It's not scary at all. Okay. Now, why did I bring up this PDF? This PDF, okay, when we use f of v, function of velocity, right, and we integrate the PDF, it helps us actually find really interesting stuff in the physical world. It helps us find fractions of V1 and V2, speeds V1 and V2 of molecules. In other words, it tells us certain fraction values of the speeds of the molecules. Okay, what fraction of the molecules calculating V1 and the speed V1 of molecule 1 and speed V2 of molecule 2, for instance. Okay, if there's any questions on that and what we're talking about here. So that's what this is. That's what this is calculating, actually. Okay. So it's pretty interesting stuff. Now, that's what this gives us. So we integrate from v1 to v2 of f of v dv. Again, v is the speed, okay, not volume, speed. Right? And so that's one of the equations that we deal with, where we have to integrate over the PDF. Another one where we would have to use the PDF, right, is in equation 3, when we have to do normalization, okay? Normalization means that I have to integrate from 0 to infinity of f of v dv, right? It's an improper interval from 0 to infinity. And all this is saying is if I integrate over my PDF3. And then we've got equation 4, which tells us that how to calculate average speed, okay? Right. So average speed, right, which is going to be called V bar on the left here. Okay, I'm highlighting V bar. Okay. By the way, take these down. Take these down for, you should be writing this stuff down, especially if you're interested in stuff. Write it down. Okay. And you can play with this for your own spare time if you're interested. You can always ask me questions too, right? But you can play around with it. And I can tell you how you can play around with these integrals. Put in values for m, pi, k, and t. Let v be changing, so that means don't put any value for v. V is an independent variable, and integrate over the PDF. Okay, the PDF that we have here from the Maxwell Boltzmann distribution. Okay, for each one of these intervals, you can play around with them. Right. For instance, this is a good one. Maybe you want to calculate. The average speed of this molecule, right? So let's say v bar here. Okay, so v bar is equal to the integral from 0 to infinity of v to the n f of v dv. Okay, all this is saying is we're calculating the average speed of the molecule. Right? So this Boltzmann's distribution has to do with the behavior of molecules in thermodynamics, and each one of these intervals, depending on what you want to calculate, comes in handy. It comes in handy for that. All right. So let me see if there's any questions. Okay, not tonight. Tonight's dead. It's because of New Year's. I probably should have done a lecture today. I find better times, not on holidays, to do it. Okay, so I think we're going to look at. Yeah, I'm thinking about it. We'll do another simulation. I think we'll do another simulation. So, anyways, I wanted to mention when it comes to Maxwell Boltzmann, velocity in 3-dimensional space, Gaussians are completely unavoidable. You can't avoid them. Okay. Since we're talking about Gaussians in 3-dimensional space, I thought it was appropriate to bring up the applications. And one of the applications I brought up just now, the reason why I brought it up is because of the use of the Gaussian, Boltzmann's Maxwell Boltzmann distribution. Okay. All right. That's why I brought that up. Okay, because the Maxwell Boltzmann distribution uses a PDF, which is a bell curve type of function, right? And all bell curve kind of functions are intertwined. Once you integrate over a bell curve, it's going to be Gaussian automatically. Okay. So let's do that. Let's look at another simulation. Okay, so simulation 8. Just give me a sec, guys. Bring up the simulation. Okay, this is an interesting one. It grabs a lot of people's attention. I'm going to share the screen. Go to Window, Media Player. Okay, so we're going to be looking at another mathematical model simulation that I made. Okay, here we're having velocity vectors, right, of a 3-dimensional Gaussian ball. Okay. Now, what this gives us is not just a mathematical representation, but it also shows the applications here, right? The applications to physics, okay? That if you have a certain type of slider, let me rewind, right? So that's why you can see it, okay? Right, so you can see we have a Gaussian, three-dimensional Gaussian ball, okay? And you can see that in our Gaussian ball, right, we can see that the temperature slider widens, okay? Either widens or narrows, depending on the size of the three-dimensional Gaussian ball. So as the volume increases, the slider widens. As the Gaussian ball, its volume decreases, right, then the temperature would start to narrow, okay? So greater volume, right? Greater volume means temperature widens. Smaller volume means temperature will start to decrease, okay? So this is very good, not just as applied mathematicians, but for scientists, though, right? This type of application really gets not just works only your mathematical intuition, uh, apply wise and geometric wise, but it also helps you understand physics too at the same time, right? Because we're playing with physical constants here. Okay. All right. So as you can see, we have a very interesting Gaussian, three-dimensional Gaussian ball. I'm gonna play part of it again. I think it's really neat. Okay. So as you can see, right, as we're getting the temperature, right, this temperature slider will widen if the volume is increasing. And as volume decreases again, right, then the temperature slider will narrow. What I mean by the temperature slider, right? Right, so as you can see here, right? Just wait for it. The temperature slider is those spikes coming out of the origin of the XYZ coordinate plane, right? So depending on the size of the Gaussian ball, either widen or shrinking. Okay, I hope that helps you guys understand that stuff in a much more detailed and conceptualized way. Let's see what's next on the list. There's one more thing on the list. We're almost done. Okay. Let's see the board. I'm thinking. Let's go back to. We have to go back to the whiteboard. Yeah, let's go back to the whiteboard. All right. Our mathematical story for today is almost done. Right. Right. We're going to be looking at that. Physics application, heat and diffusion in 3D. Okay. We won't talk about that right now. I will cut it a bit shorter, like probably 5-6 minutes shorter. It's not going to make a difference because we did cover a lot of topics. If you want to look at heat and diffusion, I don't recall, I may have a video up as well. You can look up that on my YouTube channel. This would be that or a live show, right? Talk to some degree about heat and diffusion. The other stuff is relatively new. It's pretty new, right? But heat and diffusion. Well, I talked about heat and diffusion, but not specifically in three-dimensional space. Okay. I may talk about heat and diffusion in terms of a model in 2D and in either 1D or 2D heat equation or some sort, which is related, but no, not in 3D. We knew. But I'm going to have to cut it short today, guys. Getting tired. And it's still hasn't been New Year's officially for me yet. I'm still like 2 hours behind. Okay. Around 2 hours behind. But anyways, I'm going to cut it short. I think that will be it for today. Okay. Let me think. Unless anyone's coming in. Let me see here. Anyone coming in? me see. No, I don't see one coming in. Yeah, I think we see. Yeah, we just got it right now. All right. So that's it. Now, by the way, just to remind you guys, this symmetry style thinking is, developed and curated from my book, Advanced Integration Techniques. Okay, so if you want to delve in more, you can always check out my book. Link will be in the description below for this live show. For those of you who haven't seen it, you can always inquire about it. And or if you're looking for a coach to mentor and show you how to think this way, right? You know, both strengthening your critical thinking skills, your visual spatial skills, which I showed today a lot of, or number three, and number three, sorry, and knowing the applications of the mathematics, like wanting to know the applications of the mathematics, not just the math per se, but also understanding and knowing when to use it in certain applications. You can always contact me in the link below. There's another link, S.T.E.M Online Academy, which is our coaching slash tutoring, expert coaching slash tutoring. All right, guys, that's it for tonight. Happy New Year to all. And this new year, I want you guys to make a resolution. No more calculating, but only two things: rigorous mathematical understanding, and number one, and also number two, uh, seeing, uh, geometrically visualizing and seeing the phenomenon, right? Have a good night, guys. There'll be plenty more videos coming soon. That is it. Have a good night.